You are listening to the Motherhood Unstressed podcast, and I'm your host, Liz Carlisle. Thank you so much for tuning in. I am so glad you're here, as always. And if you are in the medical field, I think you are going to love this episode. But honestly, even if you're not, you're just someone who's interested in health and wellness and being empowered when it comes to your overall health, I think you're going to really be into this episode. This week, my guest is Dr. Paniz Jasbi. He's the CEO of Theriome, a trailblazing company at the forefront of metabolomics research. Now, in this conversation, we're diving deep into the world of metabolomics, and we're uncovering the fascinating science behind how metabolism impacts every facet of our health. It's not just about weight loss. So if you're curious about the cutting-edge science that's reshaping the future of healthcare and just the profound implications that it holds for your own health journey, you're going to want to tune into this. I learned so much, and I'm so excited to share his work. It's really happening now. It really is cutting edge, so it's exciting to be sharing that information with you. I hope you enjoy it. If you do, please share it with a friend, and please enjoy this episode with Dr. Paniz Jasbi. Well, hello, Dr. Jasbi. Welcome to the show. I'm so glad that you're here.
Thank you so much, Liz, for having me. I'm really excited to get into some of our topics today.
Yeah. And I understand your hesitancy about coming on a show called Motherhood Unstressed, but we are going to get into all of the science and the just amazing discoveries that you are doing in the world. But before we get into all of that, can you talk about just the key events in your life that led you to being a researcher in health and metabolomics specifically?
Yeah, sure, Liz. Motherhood unstressed. If my mom knew I was on a podcast with this topic, she would laugh because I absolutely nothing to unstress or de-stress her mothering experience. But my mom was a big pusher in me going into science and medicine. I'm, the son of an Iranian immigrant, and there's a stereotype in our culture where they all want their sons to be doctors, and if not doctors, then lawyers, and if not lawyers, and engineers, and the great thing is that it actually aligned really well with my own interests in the world, as well as my natural inclinations. I was good at math and science, and I was good at reading and writing and debate. And for a while, I thought I'd go into law. But the idea of studying something that was sort of man-made or sort of contrived by man was less enticing to me than studying like the natural world. And so, at first, I wanted to be a physician, and I really did the whole super pre-med track and did everything I could to differentiate. And I knew in high school that's kind of what I wanted to do. And in undergrad, I worked toward that. I applied into a medical school. I got accepted, and I also got offered a research position at the same time. And so I deferred my acceptance for a year, and I thought I could come back to it. But I had such a great time in research, and then opportunities to get a PhD presented itself, and it seemed to me like that was where I wanted to be, that the sort of bedside maintenance of patients' health, which is this super, sacred and important role that healthcare professionals play. I knew that if my mind was elsewhere on research, that I was never going to do that role really well, that I liked puzzles more than I liked, being on call and having to do what physicians do. And it was really, I shadowed a lot of physicians, and I saw what they went through, and I thought that wasn't really for me. And having worked with the professors at universities and senior scientists at industry positions, I saw their lives, and I thought that was really something I really wanted to emulate and try to bring forward solutions and technologies and products and things like that. And then, in graduate school, the solutions and technologies and products and everything kind of get on hold, and you're publishing papers. You're really doing experiments, and you're publishing in trying to publish in the most impactful journals you can, with the best research possible, and very stringent review processes often. And then you kind of get bogged down in that, and you get sort of lose the forest for the trees, so to speak. My co-founder and I, and we were in the same PhD program together, and we kind of became friends immediately. And we had similar but differing roles. He's a microbiome scientist, so he is an expert in everything from the sample preparation and sequencing technologies used in microbiome science to the data analytics and bioinformatics side of it as well. And I as well, I'm trained in mass spectrometry-based metabolomics with an emphasis on data analysis and bioinformatic development. And so we really had this idea and this sort of angst that was building up amongst us, where we saw that so much of this research that, as a community of scholars, we have garnered over time, we have accrued a massive amount of data, but that data is not necessarily translating into knowledge. It's not being used anywhere. And a lot of physicians, of course, they don't have, they're caring to patients. Physicians often read abstracts, they don't read papers, and it's difficult for them to keep up on the science as it evolves. But scientists, on the other hand, that's all we do. And so we have sort of brought together our collective angst and thought of solutions. How do we make testing more approachable in the sense of direct-to-consumer kits with high analytical validity without sort of missing anything? How do we make it convenient? We're developing a web app that's under review by the App Store right now, and we should get approval. So you can do it all on your phone, interact with all of your health data on your phone, see transparently your raw health information delivered to you in one secure location. And we thought of these sort of issues, and we thought of the solutions. And how do you, a massive leap for us was, how do you digest that information? So a major roadblock for translational science, especially in the omics sciences, so genomics, proteomics, microbiomics, metabolomics, et cetera, is this high throughput data that is very hard to digest for the layperson. It is hard to digest for physicians, and that's why we use algorithms and predictive modeling, because there's too many variables and parameters for the human brain to reasonably absorb and keep track of. And so, this predictive modeling and all these things that we bring the consumer, it's sort of like an out-of-the-box researcher in the middle of your living room, and we get super simple and super easy. You collect your samples at home, you get your you take our HIPAA compliant survey online, you send your sample back, we combine your clinical and demographic data that's self-reported with your metabolomic profile, your microbiomic profile, et cetera. And we layer those the multiple layers of omics on top of each other. And then we start to see these emergent properties that aren't found when you investigate a layer of omics on its own. And then we deliver this in a really easy to understand health report format, which is essentially will be like, let's say, your gut microdiversity, biodiversity score, your alpha diversity, beta diversity. It'll be your gut compositional levels, relative abundances. And then you'll have, in your metabolites, we have 12 health domains that span your cardiovascular health, your liver health, your, integumentary health, reproductive score, aging index. And so we have combined these across 12 health domains, and we are also able to, detect in our metabolomics panel 126 metabolites. That lets us sort of multiplex them, combine them in very specific algorithms to monitor the disease states of 344 diseases that have been reported in blood. So it's also a diagnostic sort of companion test. These are tools that should be used, with the supervision of your healthcare professional, your physician, to make diagnoses. But these can be used to sort of guide physicians as to, probable causes of, sort of vague symptoms. Health domains can be used as a way for people who are healthy already to remain proactive and vigilant about that health, and to monitor it through time, and to maybe even, for some of the biohackers out there that are some of our community, they want to optimize their scores. They want to be sort of the highest in these domains as possible. And they come to us for those sort of personalized recommendations on how to improve. And then, we're sometimes giving, blood disease signature reports to customers who then go and have meaningful discussions about those potential diagnoses with their physician.
Wow. So why is metabolism and metabolomics such a great indication, such a great predictor of disease and just overall health? Because I think that that's something that most people wouldn't even consider. You hear metabolism and you think, oh, weight loss.
Yeah. Okay. great. Let's totally uncouple metabolism from just weight loss, because metabolism is quite literally the fundamental processes of your life, and they indicate everything from childbirth. They indicate anything from sperm mobility, the hair follicle health. The cancer is a metabolic disease. That is now not just the opinions of esoteric academics, but the widely held practice of physicians who treat it metabolically as well. And so cancer is a metabolic disease. Cardiovascular disease, which is the greatest killer of Americans, is a metabolic disease. This is an aberration of metabolism that, when unchecked through time, leads to CVD, cardiovascular disease. Alzheimer's is a metabolic disease. In some cases, we have started to refer to it as sort of a type 3 Alzheimer, a type 3 diabetes, where there's this sort of shift. And my own research covers this. And we have this excellent investigation figure where we show that there's this shift away from oxidative phosphorylation, first to the utilization of branched chain amino acids as a fuel source for the cell, and then later to fatty acids as a fuel source for the cell. So the idea is that these metabolic perturbations often underlie disease at the earliest stages. So Alzheimer's disease, for instance, in our paper, one of the early stage indicators was 2 fatty acids, palmitic acid, stearic acid, whose initial perturbations go back to patients with mild cognitive impairment, patients with high pathology but no symptoms, and even can be seen in patients that have no evidence of disease. So we are tracing back Alzheimer's to before symptomology and before pathology, which is typical of the brain, which is the tau pathology and the neurofibrillary tangles. And we can go back as far as, before these people have symptoms, not just symptoms that are consistent with aging, but before they have even sort of slight memory loss, we can sort of detect the potential onset of Alzheimer's. Cancer, same thing. We have, indicators of cancer that, for instance, breast cancer, which many of my papers are regarding breast cancer detection. We can look at very subtle, but when put into an algorithm with 5 or 6 of the very subtle disturbances of certain TCA cycle metabolites, which underscore the potential for a Warburg effect, or the increase of alpha ketoglutarate, which signals potential glutamine addiction. And both of these effects are metabolic typifications of cancer cells, cancer tumors especially, even in the early stage, before stage 1, that are essentially utilizing certain amino acids and certain byproducts of the TCA cycle for their own pathogenesis, for their own proliferation, cellular proliferation, angiogenesis. They use metabolite levels in certain ways to dodge immune responses. So they can actually escape the human metabolism and sort of go undetected by utilizing certain chemicals and making themselves sort of invisible to our immune systems. And that immune escape mechanisms, the pathways that are related to angiogenesis as the tumor starts to recruit its own blood supply. These are all metabolic syndrome. So wow. This is all metabolically related and can be detected. And so it's not just, are you losing weight? How do you look? Are you ready for the summer? It's really everything. It's everything. Metabolism is the total set of biochemical reactions in your body. That is what metabolism is. So everything that is building or anabolic, and anything that is reducing in a reductive sense, so catabolic. And so the total set of the anabolic and catabolic reactions, or all of biochemistry, is your metabolism. And what we do is, there's so much involved in metabolism, though, because metabolism does involve the genes. Metabolism does involve the RNA and the proteins and your microbiomes here signaling to all these levels. But when we talk about metabolomics, now we're talking about the lowest level of metabolism, and there's more of them. There are so many metabolites, and they are the smallest, right? So when we talk about metabolites, we're talking about anything that's like pretty much less than 1,500 Daltons, and that's a measure of atomic size. And proteins might be something like 40,000 Daltons, and so this is or more, much more. This is just let's say average protein, and so we have the smallest thing that we're looking at. It is also the most sensitive. So in the sort of, when we look at what are the diseases that kill people? For instance, you might have something like Huntington's, and Huntington's is an example of a real genetic disorder whereby, like, if you have the genes for it, you will necessarily develop in Huntington's. There is some disorders that are much more heterogeneous, right? And those are the disorders that kill us the most. Those are the greatest contributors to human morbidity and mortality. Those are the cardiovascular diseases, the cancers, the Alzheimer's, and neurodegenerative disorders, et cetera, et cetera. Now, those sort of usual suspects that kill most of us, those are not linked to one specific gene. There are implicated genes, there are implicated proteins, there are implicated metabolites. The idea is, however, that like these are a combination of genetic environmental factors. Their pathologies are somehow in the middle. And when you look at the hierarchy of systems biology, you have genes that are, and this is the central dogma of biology, this is what we follow, right? So we have the genes that are sort of translated to transcribed to RNA and then translated to proteins. And then from proteins, you have metabolites, right? And so in this hierarchy, metabolism and metabolomics sits at the lowest level. But if this is the gene, then, and this is the metabolism, then on the other side would be the environment. And so metabolism sits really at the intersection between the gene and the environment. It sits at that very level whereby most disease occurs, whereby most sort of responses to disease and early indicators of, let's say environmental toxin exposure or early indicators of poor liver health are going to be manifest. It literally sits at that nexus point between the gene and the environment. And gene-environment interactions are the cause of, again, all of the disorders that are the greatest contributors to human morbidity and mortality. So we are measuring this metabolism at, the metabolomics being, again, the total set of metabolites in the body, genomics being the total set of genes, proteomics, the total set of proteins, et cetera, et cetera. So metabolism is all your metabolites. And it's a very attractive level to study given where it sits in the sort of human response to the environment. And we have a panel of 126 metabolites, aqueous metabolites, and these are sentinel metabolites that are found sort of ubiquitously in so many pathways. And therefore, we get an incredible pathway coverage of the human metabolism by sort of taking advantage of the redundancy that is inherent in biology and picking metabolites that are redundant in these pathways, thereby increasing our sort of pathway coverage. Yeah. And we're able to, like I said, we report on 12 health domains. We give personalized recommendations, and all of this is analyzed, interpreted by our in-house AI. And even the recommendations are based on, the person's total metabolic profile, in addition to the clinical and demographic health information they give us. And in the future, it'll also incorporate levels of their microbiota with the introduction of our BioMe gut microbiota test. So the idea is to, again, layer these levels of systems biologies and see these emergent properties that are only seen when you have a vast amount of data across different levels of the dogma of biology.
Yeah. I mean, how sensitive is this test? Because I've heard that we all have varying levels of cancer circulating in our body, tumors, things like that, and then the body comes and takes it out. Is this an instance where you might be more prone to eventually develop stage 1 cancer and it picks it up, but then your body would have gotten rid of it anyway? Or is this like, hey, this is really coming down the pike for you. Go talk to your doctor. Here's your information.
Yeah, that's an excellent question. So for every one of our disease signatures, anywhere from 2 to 24 metabolites are monitored and matched. And so we match it with the magnitude and direction of change. Not just did it go up, but did it go up within the certain levels that we know are indicative. And we do that for all the metabolites in this one set, right? So let's say schizophrenia. Schizophrenia is one of those things where like genomics just kind of falls short. And the genes are not necessarily expressed as the phenotype of schizophrenia without certain environmental influences. And so let's say we have schizophrenia in our panel, actually, and I think there's 14 metabolites that monitor it. So we might say, or there's like about 10 metabolites that monitor it. And so we might say like, okay, of these 10 metabolites, let's model it, and let's model the direction and magnitude of the change of those metabolites. And we literally will fit, your profile to the known profile of schizophrenia along those 10 metabolites. And then we might say that 2 of them had a match. So we'll report your match percentage, and we'll say that you had a match for schizophrenia. That's 20%. And you might think, well, I have a family history of schizophrenia, and that seems normal, right? And then you come back, and then you test. You test through time. Many of our customers do test through time, and there's a lot of hidden values, a lot of latent value in that sort of longitudinal sampling, the insights we can give through time. So if you come back, then the next time it's 40%, and then the next time might be 30%. So it might be okay. And the next time might be 70%. And you might want to consider, taking some preemptive or prophylactic steps against that. We also have people who come in and they have a high incidence of let's say like cancers, right? We have cancers in our panel, as well as different types of cancers, as well as different stages of cancers. So we can match it not just on do you have, let's say markers indicative or, in the science literature consistent with pancreatic cancer, but we can say these are consistent with stage 1 pancreatic cancer, and here's the match percentage. So
wow.
And these are not definitive diagnoses, but they are a scientifically valid and cogent application of the science literature. Which again, there is a vast amount of data that is just sitting there online, and nobody, so many papers written, so many peer reviews, and it's sort of inaccessible, not just to the average consumer who orders one of our kits, but to the physicians often who could be really enabled by the application of that data, the translation of that data. And that's really where we sit, is this sort of tool for translational science and medicine.
That's huge. And that leads perfectly to my next question, is how open has the medical establishment been to the work that you're doing? Has it been more collaborative, or have you received a lot of friction because this is so new and different and might infringe upon, future profits of oncologists and things like that?
Yeah. We have had the discussion of like, well, if your test can do, all the amino acids and organic amino acids, well, that's 2 tests that I don't order because I'm ordering your test. And I'm honestly stunned at that kind of thinking. And thinking that, you're going to take a vial of blood, whereas you can prescribe your patient at home, blood kit. And so I'm really stunned at that kind of thinking, and I'm not a businessman, and I let my marketing people incentivize physicians. But overall, I will say that's the minority of physicians. Yeah. Overall, they're incredibly interested. And I love engaging with them because they can engage in the science as well. I try to keep most of my discussions fairly shallow, because there's a vast amount of technical jargon, right? Yeah. One of the things about biology is the terminology. We speak our own vocabulary, and so physicians have access to that, and so engaging with the science more and explaining things with them is a great part of my role as a chief science officer here at Theriome. And they're, for the most part, like I said, incredibly receptive to it. The AI that analyzes it and can write its own recommendations a little bit freaks them out, but we assure them that we're not, replacing physicians. That's not our job at all. Our job is to give physicians an easy to use, scientifically informed, cutting edge tool that helps them with early indicators, sort of where to look. Often a physician will have, 5 to 10 different, disorders a patient might have or diseases that could be diagnosed. And our test might limit that to 1 or 2. And so it isn't designed to replace physicians. And again, it's just meant to give them a leg up and help them digest this vast amount of information that really cannot be done without AI. You cannot give someone, here's 126 metabolites. Here are, let's say, we're going to actually get down to about 600 microbiota species to the species level L7 resolution. And we're also going to then build a proteomics panel, with 300 proteins and enzymes, et cetera, hormones in there. And so how do you give this to a person and say, there you go? The idea is that we have trained our AI to model this based upon banked and curated data. And all of our models are validated, meaning that they're not overfit to the training set. So we can apply those same weights and algorithms to new cases as we get in, new cases being our customers' cases, and then make sure that those results are valid and generalizable to their profiles. A physician cannot do, no human brain can do that. I don't mean to say a physician, human brain can do that. And so to have this vast information on a patient and have this great data set, you need to sit up on an AI on the top of that. And we have our proprietary Bayesian AI, which is performing this process of single sample profiling.
Amazing. Is this all done through open source? Are you using a company like Databricks to do all this, or is it just your own AI system?
No, so I will say something about open source real quick. It is an emerging trend in systems biology. It is where things need to go. There are amazing people doing work in open source software. The Wishart Lab, who curates HMDB. There's the GIA Lab at McGill University, who is the author and maintainer of Metaboanalyst and a ton of other software that can be used to analyze not just metabolomics data but systems biology data in isolation and in tandem. There's so many people. I mean, I can't list them all. I won't list them all. These people aren't going to mean anything probably to your audience, but they're the true, real pioneers of this work. And we don't use them actually that much. We have banked some data from both the ones I've mentioned, as well as some other open source platforms. We do take advantage of open source data, meaning enrichment sets and disease sets and citation for those and sort of analysis of those. But we've also gone beyond that in the sense of mining open source data sets that are sort of published in concert with their peer-reviewed paper. And so we mine those data sets and we also improve on the models that we have, and we create our own internal modeling algorithms. And then we apply them with our AI that is actually internal as well. So we don't use open source in our analyses. And what we generate has been coded by us, myself and my co-founder, Dr. Alex Moore. And like I said, we are we're not experts by any means, but we're proficient in data science and analytics. And he is so awesome in Python and microbiome science analysis, and he's created some great tools for Theriome. And I have some skill in R and analyzing metabolomics data. And so the suite of software analytics that we've created, they're all proprietary to us. They're all trained on data that we have either gotten from public sources as well as private or public data sets and mined information out of them. And so it is really a creation of ours and something that is unique to us.
That's awesome. That's awesome. And what are the long-term implications of what you're doing in the field of health for the American population, for the population of the world who's going to be gravitating towards early detection and prevention?
Yeah, so that's really what you described as this, medicine 3.0, right? Where and that's what we have right now is 2.0, and we're gravitating toward preventive care. We're gravitating toward identifying solutions earlier on rather than trying therapies later when the pathogenesis is present and advanced. So how does this work? We have always tried to kind of model science fiction, actually. And there's a reason for that. And when you think of, what is the best solution possible, it's always in science fiction books, right? And so we can't obviously do those things. Nobody can yet, but it doesn't mean we shouldn't sort of strive toward that. And it doesn't have to look like it does in science fiction, but it kind of has to do the same function. So a person should be able to cheaply and at least minimally invasively, if not non-invasively, monitor all of their health. And so I envision a world where, let's say it's a part of your daily routine. A little girl wakes up, takes her, Theriome test and never thinks twice about it and gets her results in a sort of a more instantaneous manner. We can't do that yet, but and sort of takes it for granted, and she can monitor things, and everybody does this, and it's just an integrated part of our lives. And for it to get there, it has to be, very easy to access. And so we're working on ways to, we already have our direct-to-consumer health testing. We have our, advanced analytical platform. You normally cannot get 126 variables from a few drops of blood, but with our platform, which is a gas chromatography mass spectrometry platform, hypersensitive platform, meaning it can, investigate at down to the, picomolar, sometimes femtomolar levels. We're dealing mostly in the micromolar scale on our test, but the system with optimization can be even more sensitive than what we're using it as. And we're able to get a vast amount of information, and with advances in computational technology in the last 10, 15 years, we're now able to analyze that data. There was, the development of these technologies did not happen in perfect parallel. So as the platforms were evolving, techniques like NMR and mass spec and next generation sequencing, these platforms were not necessarily met with concomitant increases in technological capability or analysis. So that had a little bit of catching up to do. So we really had sort of like a two-step process to getting here, whereby first we had to be able to detect so many biological variables of interest, and then add relevance to them through being able to analyze them. And we're now at a point where we can do that with such precision and with such remarkable accuracy that we again, my co-founder and I, we really felt like now was the time to introduce these products, and it should go from being sort of the ideological fantasy of academics to the practical application and a tool for everyone to use. So we're always striving to make it more accessible. We're always trying to make it more accurate, more integrated, faster response times, and there's a ways to go. But I'm confident that it probably won't even get done in our lifetimes. But I'm confident that with chronic application, that we can get people to sort of realize the value of systems biology testing, and realize that it's really that looking through the whole rather than as a synergistic thing, rather than just the sum of its parts.
I love it. I love it. And we are almost at the end of time here. So if you have anything that you'd like to leave with the listener about the work that you're doing, about your journey, about your company, now's the time to do it. What would you like for them to remember?
I'd like you guys to remember that, the current health monitoring and diagnostic capabilities we have are woefully inaccurate. They are sometimes woefully misapplied. And most people are not monitoring their health on a safe or regular basis. So I would always, this isn't to make anyone paranoid. Most people are healthy. Most people who even take our tests fall within normative ranges for most scales. But I would say, grow to appreciate the complexity of biology, and realize that sort of a high level of one thing or the other might not necessarily mean anything, but it is, again, those emergent properties that can only be seen through taking such a vast approach, where we begin to see really interesting and personalized metabolic signatures. So I would say just sort of be on the lookout, because I think this revolution is coming. There are other entities that are performing similar, if not different, testing than us. And I think we're getting to a world where physicians, insurance companies, the pharmaceutical industry are really starting to appreciate and invest in systems biology, especially in concert with advanced machine learning algorithms. And we're going to see that sort of brought to the forefront more and more. So keep an eye out for that.
I love it. And you are a true pioneer in that. Your mother would be so proud.
She's proud now. She's proud now. Not when I was kinking out in high school. That was a little bit too much stress for her, but proud now. And thank you, Liz, so much for having me on. I really enjoyed talking sincerely about the work we're doing at Theriome. If anybody has any questions, they can go to www.therio.me or info. You can email us at info@therio.me. So thank you so much, Liz, for having me on. It was a pleasure.
Absolutely. And as a complete layperson, you explained it so well. So I'm confident that my intelligent audience will understand it too. So thank you for taking the time today.
Absolutely. Thank you again.